We are discussing on a case study that was the development of MEMS accelerometer, that is piezoresistive accelerometer, and in my last two lectures I have discussed in detail on the design aspects of the accelerometer along with the external circuits necessary for characterization the accelerometers. Today's lecture is on the development of the technology of the MEMS piezoresistive accelerometer. How the accelerometer is designed, that has been told already. Now, the technology development as well as packaging and characterization, how it can be done, that will be discussed in today's lecture. Then the case study will be completed. So, for designing accelerometer, the end of the design process is making the mask. Mask was not discussed in my last lecture. Today I will first initiate the discussion on the fabrication of mask, and then we will switch over to the technology development. Now, for the layout of the mask, here first you have to design the resistance, piezo resistance, and so far the design is concerned is same as the design, resistor design used in integrated circuits. Already you know how in IC resistors are designed. You have to know the seat resistance of the layer which will give the desired resistance value. Now, if you know the seat resistance, then you have to select how many number of square are required to get that resistance. And in our design we found that our resistance value is nearly 1.5 kilo ohms, in that range. But one thing I would like to mention, that in any diffusion technique the resistance variation after fabrication is nearly 10 to 20%. In most of the ICs are designed in such a fashion that even 20% variation of the resistance values will be accepted by the designer. That means design should be robust, so that with that resistance change the performance of your circuit will not hamper much. Similarly, here also we assume even 10-15% variation, the complete circuit should work. And in our case, so far the IC is concerned, that is mainly the resistance bridge, and interface electronics we will separate at outside the chip, because we are not going to have the smart piezoresistive accelerometer sensor, acceleration sensor, rather the multi-chip module we are thinking. So, first if we discuss on the resistance, we have, you remember the seat resistance value we have assumed is a 250 ohm per square and junction depth is 2.5 micrometer. So, there you can see the diagram in the left side. So, there the width of the resistor we assume it is a 20 micron. So, accordingly length we have decided 120. So, 120 by 20, so it will be 6, and then it will be approximately 3 kilo ohm type, and the contact pads in both the side will give 0.5 square also. So, in the total resistance value will be, should be nearly say 2.1, it is nearly 1.5 kilo ohm, I think 1.5 kilo ohm. So, now if we connect two resistance in series, it will be 3 kilo ohm. So, now this is the contact area in the second diagram, it is 20 micron by 20 micron, it depends on your technology, but here we have taken the robust values of 20 micron by 20 micron, so that in future we will not have any problem. So the contact is the second diagram is the contact pads, and the overall the structure looks like that. Now after the piezo resistance layout, then we will go for other layouts, that means etching. You are going to etch and metallization. So here basically it will be nearly masks are nearly 4, but another 2 masks are required. So that is for your the glass etching mask is required, as well as some passivation mask is also required, that is not included. Fabrication of the middle layer, which is the sensor, for that you need the 4 layers, that is mask number 1 is the resistor mask, mask number 2 is backside etching mask, mask number 3 is front etch and contact window, mask number 4 is metal line, and mask number these are the 4 masks, and if we all the 4 masks are overlapped, then it looks like that, all the layers together. So a resistance mask, one resistance looks like here, it is shown here, and backside means one front one backside mask is required, because you are going to etch the complete thickness of the silicon by bulk micromachining technology. So here initially from back some of the layer is etched, so that is using the TMH, and the front also, if we remove the silicon dioxide from selected portion, so when you put in the etch bath, then completely the from some of the region it will attack from front side and back side, and thorough hole will be there, and in the front edge mask where it is protected, so particularly in the flexure region and the proof mask region which is at the center, so that portion we have to protect it, so that from the front those regions will not be etched, but from the back it will be etched and it will stop somewhere means the flexure thickness. So just by deciding how much time required we will give you for front edge and back edge, so your flexure thickness will be determined from that time management. And these are the interconnection layer, because Houston's bridge we have seen there are 8 resistances, so you have to connect 8 resistances such that you can get very low off axis sensitivity. So here the resistance lines are moving from one end of the bridge to one end of the frame to other end of the frame, and there the lines are routed in such a fashion that there should not be any overlap. So we have not used any underpass resistances here, and we have used single level of metallization. So some tricks you have to follow, so that the metal lines will move in such a fashion, 2 lines will not touch each other or it will not overlap. And there are 4 bond pads required, one is 2 are for power supply and 2 are for output. And here you can see there are 5 bonding pads, 1 extra bonding pads has been given here, that is for substrate contact. So the substrate should not be floated, substrate should be grounded, otherwise if it floats, so there may be problem of stability during the measurements. So that is why 4 bond pads, 2 are meant for power supply, 2 are meant for output, and 1 is for substrate contact. So these are the complete layout, and along with the bonding pads is shown here. Now the fabrication process. So fabrication process, first step you have to specify the wafer, and we are going to use silicon 100 N type, because we are going to make a resistance P type diffusion, and resistivity of the wafer is 4 to 6 ohm per square, thickness of the wafer 270 micrometer, plus minus 5 or 10% variation is there, and is a double side polished. And this is 2-inch diameter wafer. 2-inch diameter wafer, is the thickness is roughly 280 micrometer. plus minus 5 micrometer already tolerance is there. So, this is the basic wafer, and then after taking that wafer you go for oxidation, and that is called initial masking oxidation, that is 20-minute dry oxidation, 120-minute wet oxidation, another 20 minutes is again dry oxidation. You know, normally any sort of masking oxidation we follow dry, wet and dry sequence, so that quality of the oxide is good as well as it will not take much time. And it has been done at 1100 degrees centigrade, and if you follow this sequence the thickness is expected to be 1 micrometer. Now, after masking oxidation we are going to use mask number 1. Mask number 1 is oxide patterning for boron diffusion. That means first step is to fabricate the resistances, and the resistance location already found, and accordingly mask has been designed, maximum stress region they are located, resistances are located. So, oxide patterning for boron diffusion, for resistance we are going to use the boron diffusion, solid source diffusion. Source is boron nitride cake, and from there are 2 steps we will follow. First is pre-deposition and then is drive-in, and boron pre-deposition diffusion we follow 15 minute 950 degrees centigrade, and there the sheet resistance is approximately 90 ohm per square. So, with that step, next is LTO. LTO is a low temperature oxidation. In particular boron diffusion, normally in between pre-deposition diffusion and drive-in diffusion we follow a step which is known as a LTO, low temperature oxidation. What is the requirement of that particular step? We use this because we have to remove some boron stain. During the pre-deposition diffusion, using the boron source, boron nitride cake, a boron stain, that is borosilicate glass, a very thin layer of borosilicate glass will be deposited along with pre-deposition diffusion. This thin layer of borosilicate glass is very difficult to remove afterwards, means after drive-in, and in drive-in we know there should not be any source of boron from external side, only whatever has been inserted into the silicon that will redistribute, that is the objective of drive-in step. But here if we do not remove that stain layer of boron, then they will act as a source during the boron drive-in process also. So, in that case the sheet resistance will change, it will not tally as per your simulation results. So, that is why in between the pre-deposition diffusion and the drive-in diffusion, whatever the boron stain is formed, that has to be removed, and that can only be removed if that borosilicate glass is completely oxidized. That means we have to go for a very low temperature wet oxidation, 30 minutes 750 degrees C. So, with that the whatever the borosilicate stain layer is formed on the surface of the silicon, that will convert it into silicon dioxide, and after that you give an buffer hydrofluoric acid a dip, that means etch that this boron stain by buffer hydrofluoric acid, then clean it, it will be the surface boron source from the stain will completely be removed. After that you go for boron drive-in, and that boron drive-in we follow here 100 minute of drive-in and 1125 degrees C. Okay, that is basically the oxidation and annealing together, and because of that you know the impurity which has been inserted by boron pre-deposition will redistribute, and it will further go along the depth of the silicon, and junction depth will be decided by the boron drive-in process mainly. And after drive-in is completed, the expected sheet resistance is 250 ohm per square. Now, next step is the again lithography. During the drive-in process we know we normally fabricate a thin layer of oxide that thin means it's not thick as the initial masking oxidation, that's why I am calling it thin, and that is nearly 5000 to 6000 angstrom unit, and that is adequate for subsequent the lithography step. And there we pattern the oxide for backside silicon etching, that is the mask number 2 is for backside silicon etching. Okay. So after that again we go for lithography with mask number 3. Mask number 3 is oxide patterning from front and CW is contact window and front side silicon etching. Okay. So backside lithography we did it, but after that in mask number 2 in the previous slide, after that we didn't go for the complete etching. Okay. Then subsequently go for, because it is double side polished wafer, we go for the mask number 3 and lithography there, and after lithography then front side silicon is etched little bit, oxide is removed in the lithography, then the silicon is etched, that means you define where the holes, complete holes, thorough holes is to be made, and here it will protect the probe mask region as well as the flexure region. And you should not go for long time etching, because then the surface will be completely irregular, means there will lot of ups and downs, and then metallization may be a problem. So few hundred angstrom, or say at the most 1 micron or 2 micron you etch it. After that you go for metallization, and there aluminum is deposited and patterned, and aluminum thickness is 1 micron. Then this aluminum will remain on the top, and in the top and bottom both places we have defined the regions where silicon is to be etched by using lithography mask number 2 and mask number 3. Then the metal, after metal patterning is over, that is the mask number 4, then you go for anisotropic etching. This etching in 5% dual doped TMH at 70 degree centigrade. Dual doped TMH etching has been explained in detail in my micromachining lecture. So we used the 5% and temperature we use 70 degree C from both sides to release accelerometer structure and define flexure thickness, and flexure thickness is we designed for 20 micrometer, but exactly 20 micrometer you may not get it. After thickness etching you have to again measure the thickness of the flexure, it will be nearly that thickness. So that whatever thickness after etching you are getting it, so with that thickness you have to recalculate or re-estimate again how much will be the output voltage of the bridge, and it, so obviously whatever the stress values you have defined earlier during the design, it will not be the same if the flexure thickness is different. And flexure thickness, exact flexure thickness you cannot get until unless you go for this the doping selective etching or electrochemical etching. Here what we follow here is a time etch. So time etch disadvantage also I mentioned in my lectures on micromachining, that here all the flexure whatever you need the thickness, that may not be available. If you go for time etch, some variation will be there because of uncertainty in recording time of etching. Anyway, so the etch rate of the TMH at 5-8% dual dope is a 0.8 micron per minute, and how much thickness you have to etch, how much silicon thickness you have to etch, so that you can determine, and accordingly you can dip the complete wafer into the TMH solution for that time. So now how the process flows, then that I will show you, that will give you a complete a full-fledged idea of how this thing is going on. Now we know this left side is a you can see here the structure of the, in the left side is the structure of the accelerometer, and along A dash we are drawing here the cross section diagram process flow. Now initially the end silicon wafer. Now what is done, the oxide is grown. When you grow the oxide, it will be from top and bottom, both side oxide is there. That oxide is grown. In the next step, we just lithography for piezoresistive formation. That means front side lithography you have made, so that you open the windows from the top side oxide where the boron is to be doped. Then the boron diffusion, P deposition and drive-in diffusion we made. So you can, the pink color regions are the boron atoms which has already inserted into the silicon wafer. Then we go for the boron drive-in, initially the pre-deposition and drive-in. During the driving process, whatever the grooves followed, and that will again cover. So that means oxide, both front and back side will cover the silicon, bare silicon. So that is after boron drive-in, it looks like that. Next step is the lithography for contact and front side etching, that you can see here. The contact has been opened, and the oxide was etched, and the front side is defined. Now next we go for the lithography for back side etching using double side alignment. So wherever the resistances is there, and you have to see those regions, because all the diagram which you can see here cross section along A dash, which is shown in the right side of the middle sensor structure. So the bottom side also the oxide is removed. Then in the next step you can go for the aluminum metallization and patterning. So aluminum metallization, the green levels are aluminum, along the cross section diagram it is again. So now you can go for the silicon etching in dual dope TMH. So it will looks like that. Since the structure is only along A dash, so the front side, the etching front side, particularly the periphery of the probe mass is not shown here. That whole diagram is along A dash. Okay, that's why you can see only the back side etching, only front side etching part is not shown here in this diagram. So with that you can get the cross section along A dash like that, and this is a 2-inch wafer in the about 12 pieces. You can see the accelerometer, the front view of the complete wafer is shown here, and one individual structure is in magnification, it is here. You can see the metal lines, how it is moving over the flexure, and the bond pads are also shown. Okay, the individual wafer is, individual piece of accelerometer is shown in the right side diagram, and the complete wafer is shown here in the left side diagram. Okay, so this is the thing. So here some photomicrographs are shown of on different places. So you can see this is the SCM micrograph. So the picture 1 shows the aluminum metal line, how it moves, and the flexure. Particularly this picture is shown to show you how the flexure has been made. And another thing is to be, one important point is when you are make the design, particularly the probe mass design, then you can see the corner. I have mentioned you earlier that at the corner etch rate is faster. So that's why you have to, in all such design, you have to allow a corner compensation. That means since corner etch rate is more compared to the lateral or vertical etch rate in the side. So what normally is done, you can see here. So this is basically the flexure. Now this corner you have seen that it has been etched, and ultimately it is rounded here. Similarly here also rounded. But if we need the perfect square structure, then what is normally done on the mask side, you have to make a corner compensation structure, something like that. So if you make that, so it will attack from this side, it will attack from this side, that side. So ultimately it may end up in a complete square. So that corner compensation is given, so that here you can see that is the almost nearly perfect. You have got it. The otherwise if you don't give the corner compensation, then it will be look like that, because it will etch more at the corner, this corner, this corner, and this corner. but the complete square structure you cannot get it. So that is one point I have not mentioned earlier, but during mask fabrication that you have to add. And this is the flexure dimension. How the flexure has been made, that is shown, is a SCM micrograph also. This length is 10 micrometer. So from there, if you scale it, so you can easily measure the thickness of this flexure, and this is the width of the flexure, you can easily measure. So this is a micrograph of the flexure, and this is the 12 pieces and one piece is shown, and this along with the metal lines. Okay. Now so is first you have fabricated the middle sensor, but accelerometer structure you have seen there are 3 pieces, 2 cap layers are there. For your damping analysis you need upper cap layer and bottom cap layer has to be delineated, is delineated, so that during the movement of the middle probe mass, so the proper damping is to be made by allowing certain gas or air with certain pressure, certain viscosity in between the gap between the probe mass and the bottom and top cap layer. So next step is to design and fabrication of the top and bottom cap layer. So top and bottom cap layer normally we make out of the glass, Pyrex glass is normally used, and how the glass is again micromachined and structured so that it will be just covered top as well as bottom, and from the top cover the bonding pad is to be separated out, because if you cover the bonding pads, there is 2 input and 2 output and 1 substrate contact. If you want to connect those things, so those portion is to be left when you are going for the substrate to glass bonding. So for that you have to again design the mask for the glass etching, and a bonding technique is used, silicon glass anodic bonding technique, which will help you bonding of silicon and glass, and the substrate bonding and details of the mechanism of bonding will be discussed in some other lecture. So here what we follow, and basically that follow for etching the glass, that only I will discuss. So in all MEMS devices we need that, except say few cases, most cases means like thermal sensor, you may not require top and bottom glass coverage, but most of the inertial sensor we need some cover plates either from top and bottom both, or only from the bottom in some cases, not from the top. In pressure also you need, if you need the absolute pressure or relative pressure, accordingly you have to select whether you will cover both top and bottom using the glass plate or either bottom or top. Now again glass to this is 2 purpose it serves. One purpose is protection of the sensing element from outside and hazardous environment. So this covered not only this, it in accelerometer particularly it is for damping it is required. There are in other cases also we use some encapsulation or the passivation layer, that you know that is used only for the reason. What is the reason? Reason is protection of the chip from the environmental hazards. Okay. So here the glass and silicon bonding has been done using the anodic bonding technique, and that basically if we apply a voltage of the order of say 500 to 1000 volt and increase the temperature of the glass and substrate to 350 to 450 degrees C, then the silicon and glass will be bonded together, which you cannot separate. That is known as the field assisted bonding or anodic bonding. And this is very sensitive technology in the respect that when you bond the silicon and glass, so surface of the silicon and glass is to be extremely clean. If it is not clean, contamination is there or not smooth enough, so bonding will not be proper and it cannot be sealed. Another point is to be noted, the matching of the thermal expansion coefficient, that is also a problematic thing. And sodium rich glass should have the equivalent thermal coefficient of expansion as silicon, which is 3.253 10 minus 6 per K at 400 Kelvin. So, if you go for 400 Kelvin temperature during the bonding, so there the matching of the expansion coefficient is also important, because after that when you cool, it will crack, the bonding regions will be cracked and sealing will not be the proper. So, these are the 2 points, one is the matching of the expansion coefficient and other is the cleanliness of the surface of both glass and silicon where you are making the anodic bonding. So, with that this is one kind of bonding machine. You can see here whole thing is to be done in a vacuum chamber at low pressure, so that the environment hazards will not be there. In vacuum chamber there are 2 electrodes where you can apply voltage, and at the same time you have to heat the substrate in the range of, as I mentioned, 3 to 400 degree Kelvin, and then if you allow certain time and it will be automatically bonded, anodic bonding will be there. This is some indigenous equipment made in our laboratory for preliminary studies on the silicon glass anodic bonding, and later on we have also procured a very good machine, substrate bonder machine, and that will help, and there are a lot of the preventive measures has been taken in that advanced machine, substrate bonding machine, which we have recently bought, and there you can bond the anodic bonding or thermocompression bonding or some other kind of bonding are also possible, fusion bonding, that is also possible. Now, so here that means the system is to be evacuated, DC power has to be supplied, and temperature is to be increased. So, accordingly the whole system is not so simple, it is complicated. In a vacuum system, if you heat the substrate at a high temperature and with a high voltage, so automatically the whole module is not so simple like the normal evaporation system, vacuum system which you use for aluminum or gold evaporation. It will be complicated. Anyway, we have done it. Now, some other points are also mentioned here. Since the glass is composed of silicon dioxide, the glass etchant should be HF based solution. Now, that part which I discussed is the bonding part, but now the glass etching, glass micromachining, how do you do it? So, glass is nothing but silicon dioxide, so obviously its etching solution will be a hydrofluoric based solution, and then you have to mask the glass, and if you etch the whole thing by the hydrofluoric acid, then thing is that you have to have some protective layer. Photoresist layer may not withstand long time in the hydrofluoric acid solution which you can use for etching glass. So, we go for another the passivation layer for glass etching, that is chromium gold. Chromium gold metal mask, gold is a metal, so is better solution, as the hydrofluoric based solution will not allow you to use photoresist as a masking material. So, the etch rate variation of different concentration of HF solution at different temperature has to be made before glass machining. So, if you use the glass, how the gold, chromium gold layer is useful for your etching, to know that part you have to go for a systematic study of what systematic study, that is etch rate variation with temperature and concentration of the hydrofluoric acid. So, that has been made, and this is the micrograph of the etch cap layer. You can see this is a glass piece has been just etched in different pieces, and in the middle portion also thinned down about say 20 micrometer gap, which we have calculated during the damping analysis, that has been made. So, now these are the etch rate of the glass at different concentration. The calibration curve is shown here. the concentration versus the H rate, and bottom is the temperature versus H rate. So this is almost linear nature of curve, which is good, and from there you have to take certain concentration and the temperature to etch your glass, and automatically if you know the etch rate, the timing is also fixed to how much you want to etch. Depending on that, you can allow that time for etching glass in hydrophobic solution. So this, for that, these calibration curves are important. Now this is the process steps for fabrication of the glass cap layer, and here you can see from the first the cross section diagram is the glass substrate. Then what you have done, the chromium film that is required for gold adhesion, few hundred angstrom unit, and top of that is a gold film, and now the gold film is this pattern. After patterning the gold film, the chromium is the bottom, it is still there. Then you go for the photoresist cover, this is a photoresist, and after photoresist cover, then a particular region you remove photo, because each window opening you require a photo masking. So you etch this particular region, and first photoresist is dissolved, then the gold already removed in earlier diagram. So then chromium is removed, and then you go for etching, and then you will etch little bit on the glass, not the complete, some portion is etched. You can see next phase what has been done. So here window is open. After this region, the left side of that another window, which was the gold was removed earlier, so that portion is open now. So now here also you started etching. During this step, here also it will continue etch. So here etch depth will be more, and compared to the side depth. So here, and then you remove the photoresist as well as the chromium layer from the whole region where the proof mass will bend that region. So now you again go for glass etching. So as a result of which, since you have open window at the very beginning this region, so automatically what will happen, so this particular region will completely thorough hole will be there, and here the etch depth will be less compared to the thorough hole region, and subsequently which you have opened at the later stage, there the etch depth will be nearly 20 micron. So why I made like that? Because somewhere I made thorough hole, somewhere I need this scribe line. So that's why I opened the windows in different times, and at the end when we go for etching, it will etch all the layers, somewhere thorough, somewhere scribe line, and somewhere the desired delineation you will get it. Okay, this is the process steps of making the glass cap layer. Then here the picture shows the middle layer is shown here. You can see this is the middle layer. So now in the left side and right side are the two glass pieces which we etched and separated, and in this you can see the size of the glass piece for 1 and glass piece 2 are not same, different, because one is at the bottom you need the complete size, you need the glass, this is the complete size, and in the top it is smaller size. Why? Because you need the bonding pad region to be excluded from the cover. So if you put the bottom layer at the bottom and the top layer at the top, so then it looks like that. So you can see here, this is the glass layer, that is the layer 1, and in the bottom is the layer 2, and in between this is a layer 2, and in between you can see the bonding pad regions are open, so that you can take bonding here, 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 and here. So these are 4 bonding pads required, 2 for inputs and 2 for input means a power supply, and 2 for output, that is excluded, that is outside the glass cover. So with that, this is up to this you have just substrate bonding, substrate to glass bonding is over. Now in the next step you have to package it. So you see, again I have repeated, this is the middle layer, this is the middle layer. So middle layer is this one. Now top and bottom cap layer you have bonded, this is this one. After that, what is the next step? The step 1, step 2, then next step, step 3 is here. So, that is this is step 3, that is the wire bonding. So, you see the bonding pads 1, 2, 3, 4, if you see minutely in the figure. So, bonding pads are connected, one here. So, one here and another is here. So, this one is here. So, okay, and one is substrate contact. The 4 bonding pads, after this is the encapsulated the case, and on the case is a metal can basically. First thing is the whole chip, which is shown here, glass, silicon glass, is to be fixed at the middle, and then wire bonding is done, then top cap layer. If you put the top, this is not the sensor cap layer, but it is the encapsulation. The top metal can encapsulation is covered, then the complete the accelerometer looks like this. This is the accelerometer, with this is the leads, and this particular package is not ideally meant for this accelerometer, because here you need only 5 bonding pads, but you can see how many pins are there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is 22 pin. So, it is a 22 pin package basically, and you need only half of that, this portion, but commercially available package with only the 4 or 5 pins and internal size of the diameter or internal size of the accelerometer is not available. That is why we use that particular package, where you can use double chip into the same package. Here also you can put another chip, so that 2 things can be done on the same package and for different applications. Okay. So, this is the package. So, after packaging is done, what is the next step? Next step is, this is another kind of package is shown, that is also not meant for that accelerometer, for basically the big VLSI chip, but since the standard the custom package was not available, we tried with this also initially for some testing, and that is why we have seen 2 packages, and this is with cover with encapsulation. Now, the next part is the interface electronics. So, interface circuit, for characterization of the accelerometer, we need what we need? 3 things we require. One is the offset null circuit, because the resistance values will not exactly same, which is designed. So, in different arm the resistance values may differ. So, because of that you will get some offset value. Offset means when you do not apply any acceleration 0G, so the bridge is perfectly balanced and output should be 0, but that will not be there because some mismatch of the resistance values in different arms. So, that has to be cancelled before you go for actual testing. So, for that you can use a circuit for offset null circuit, and that has been shown in some of my lectures, the electronics circuits. And the next requirement is the amplifier, and we used here chopper stabilized, the instrumentation amplifier has been used for that particular purpose, because that reduce both 1/f noise, because you know here the sensor signal is very low frequency and almost DC to and maximum is nearly 100 hertz or something like that. So, low frequency DC signal is to be amplified, so without incorporation of much noise. Okay. And for that the chopper stabilized instrumentation amplifier is ideal, and some such the amplifier module is available in the market. We can connect that. The Wheaton's bridge is shown here, R1, R2, R3, R4, these are basically the bridge resistance, and is connected with the amplifier and the offset null circuit, all has been connected, and that is shown in this diagram, the test board along with the interface electronics. So, this is the package, this is both the packages shown, one package is here and another package is here. So, now these are the you can see the TC7652, that is the chopper stabilized amplifier, and 2 trim pots are connected in the board, and that is basically for exact nulling of the offset, because some external trimming arrangement is also there, so that different accelerometer may have different offset voltage, so that you should have some external control, so that you can get exact null with 0G condition. For that these two trim ports are connected, and its amplified version, this amplification is made so that you can get plus minus 6.5 volt output. That was the initial specification. And if you go in the next stage, then you can see the sensor bridge will provide a differential low frequency less than 100 hertz, low amplitude less than 20 millivolt signal, which is to be amplified within plus minus 6.5 volt peak to peak. The resistance values used to achieve plus minus 6.5 volt are R1, R2 equal to 1 kilo ohm and R3, R4 equal to 500 kilo ohms. Above design amplifier using TC7652 configuration provides stable output up to 200 hertz. The calibration is linear, providing a gain of 306.67, which is nearly 25 dB. With this configuration, the signal handling capacity of the amplifier is 54 millivolt. That is the test board which is made. So now the characterization. For characterization means initially we have to measure the individual resistances. So that has been measured on bare chip, and 3 devices has been made, and you can see for different arm. So 1 to 4, 1 means this point is 1, this is 4th band point, 2nd band point and 3rd band point. So 1 to 4, if you measure from here to here, the resistance value is 2.56, and from 2 to 3 it is 2.569. So this should be equal. So you can, although 2.5 in the second decimal place, little variation is there. Similarly 1, 2 and 1, 3, it's nearly 2, 2.028, 1.96, 2, 4 and 3, 4, 1.87, 1.98. So it should be exactly equal, but it's not there because of slight variation of the resistance values. Device 2 is also similar, 2.74, 2.71. So if you look individual values, say the values are almost equal with slight variation. Because of that, you are getting the offset value, and variation in resistance values from the theoretical values is found in nearly 10%. Whatever design, and these are the measured value, and we got nearly 10% variation of the resistance. That is always allowed, and because of that we are getting the offset voltage. Now individual resistance has been made. So individual resistance, whatever design 1.5K, but we are not getting it. We are getting is 1.34 kilo ohm, 1.36. So 2M, the frame ends 1M, 2M, 3M, 4M, 1F, 2F, 3F, 4F. These are the mass ends, M, and F stands for frame end, and the connections are like that, which is shown here. So individual values are also measured, and we found that variation is also within 10%, but it is not very wide apart. So that shows that there is a possibility of that we may achieve the targeted value of the design value of the accelerometer. So now these are some other measurements. This is the measurement results of the accelerometer chip with interface electronic setup. This is the offset. So initially, if you don't use that offset null circuit that is shown with the power supply variation 0 to 15 volt, we got the offset bridge voltage is nearly 400 millivolt. So 400 millivolt is very high offset value. So you cannot use that particular bridge for sensing. So we connected that offset null circuit in the test board, which I just now have shown you. So there, with incorporation of that offset null circuit, we got here the offset value reduced at 15 volt. It reduced to only 10 millivolt. Initially it was 450 millivolt, 10 millivolt, but power supply is not 15 millivolt. We are going to use only 5 volt. So for 5 volt range, we have seen only up to this region. If you see here, so here the offset value is nearly 0.2 millivolt. So since it is a 0.2 millivolt, so that is acceptable for further measurement. Now next step, we did some acceleration measurement. Only z axis measurement is shown here, and 0 to nearly 10 or 12 G we have measured, and we found is highly linear. This is a measured value after packaging. This is a dynamic testing, and the experimental is a value and best fit curve is shown here, and here the offset we found 0.06 millivolt in this particular case, and in the second curve is the negative acceleration. This is a positive acceleration means one is acceleration, other is deceleration. So that in both the cases we found from 0 to 13 g, for which we have measured. So in both the cases we found is exactly linear curve, and that is highly desirable, and the output voltage we are getting is nearly 500 microvolt per g. So mean acceleration output we got 506.22 microvolt per g. Percent linearity has been calculated, and if you use the maximum deviation, then we are getting 0.88%. If we mean deviation, then we got the linearity is 0.253%. So the linearity allowed in design is less than 1%, and we got the targeted value. It is well below 1%, and output is 506. And here we are not getting the output as per your design value. The reason is that there we have designed the flexure thickness of only 20 micron, but later on we measured the flexure thickness is nearly 30 or 32 micron. So because of the variation of the flexure thickness, here also, because flexure thickness thicker means you will not get much output. Output will be lower because it is not that much sensitive. So because of that, we got a reduced value of the output per g. Now the next is a off-axis acceleration measurement, that also we have made. Here along x-axis acceleration, along y-axis acceleration, the curve is shown here, and that value is extremely small compared to z-axis acceleration. Z-axis we got nearly 500 microvolt per g, but here you will get the value is a nearly 26 microvolt per g. So that means it is highly 500 in z direction 500 microvolt, and x and y direction only 26 microvolt per g. So off axis sensitivity less, but we have to agree the fact that it is not as low as design value, because of various reasons of the fabrication tolerance is not exactly so, which is required, which is estimated in our design. So accordingly off axis sensitivity is not that high value, but it is 500 is 26, at least more than one order less. Okay. So now if you see the resolution studies of the accelerometer, then you can see here we can measure the resolution in the z direction up to 0.25. This is a 2.2, 2.25, this is 2.3. Here you can see 0.05. 0.05 g we could resolve because you can get the z-axis accelerometer difference 1.197, 1.225 here. So difference is there. So that means up to 0.25 g you can resolve, but again it could be resolved in a further low, but because of the measurement facilities not available to give milli-g acceleration, that could not be measured. That is the limitation of our test facility. But here still we can find that up to 0.25 g, means 250 milli-g, it is resolving. Okay. So anyway, so that is some of the negative and positive z-axis, the resolution has been studied. So with that, actually let us conclude that what we did today in today's lecture. So how the accelerometer, piezoresistive accelerometer is fabricated, that is discussed in detail, and the technology optimization has been done. Offset voltage circuit shows that within 5 volt the offset can be reduced up to 0.2 millivolt using external circuit, that is also possible. How to make the upper and lower cap layer from Pyrex glass, that has been discussed in detail, and accelerometer packaging, substrate bonding is shown, and the external circuits are also connected with the main sensing element, and at the end it has been characterized with the limitation of characterization facilities, and all these things shows that although it is not exactly the same as the design value, very close to the design value we achieve the target specifications. And with this I can conclude this lecture, means case study on the fabrication of MEMS accelerometer using the piezoresistive pickup technique. Thank you very much. Today we will discuss on MEMS capacitive accelerometer. In my last lecture, last few lectures, I spent on MEMS piezoresistive accelerometer, a case study that is particularly for avionics application. We just described how a accelerometer is designed and then what will be the technology, fabrication steps and its characterization. And today I want to spend on another case study, that is MEMS capacitive accelerometer, that is for generalized application for defense and many other automobile sector also we require such accelerometer. So, MEMS capacitive accelerometer, a case study, that is the topic of discussion today. Now, the design specifications of that accelerometer is, a range of the accelerometer is plus minus 10 G, over range is 30 G, that means up to 30 G there is no destruction of the device, it should withstand. Damping ratio is 0.7 to 1.2, natural frequency is 100 hertz, nonlinearity plus minus 1% full scale, resolution 0.02 G maximum and threshold is 0.01 G maximum. Operating temperature range is minus 85 to plus 40 degree C. So, now with this specification, how do we proceed to design a accelerometer which is based on capacitive sensing. Now, the structure of the capacitive accelerometer is shown in the figure here, you can see, and this figure is 3 modules. You can see in the middle piece is basically the sensing element and it comprises of a proof mass which is also known as a seismic mass, which can move freely between 2 fixed electrodes. What are the 2 fixed electrodes? One is held at the top and another is held at the bottom.